To the video on Faraday's law and Lenz's law. This is actually the main part of this whole chapter. So let's look at this picture on the left right here. So it turns out that what happens when you move a magnet into and out of this loop in this way, so moving it this way or this way, you actually see that a current happens in the loop. So no battery or anything in the loop. This is an ammeter. It's completely passive. There's no, this isn't an energy source or anything. So you're actually creating a current by moving this magnet in and out. Motional EMF doesn't really explain this because, all of the charges in this wire are at rest. So there's no magnetic force on those charges, and it's not really a motional EMF thing. So motional EMF can't explain this. We got to talk about something new, or really we're going to generalize what's going on with emotional EMF in Faraday's law. So Lenz's law is all about finding the direction of that induced current. So we'll talk about the magnitude of the induced current and the induced EMF in the next section when we talk about Faraday's law. Lenz's law is all about just the direction of the induced current. All right. So first of all, notice that the magnet here has its own magnetic field. So from the loop's perspective, this is like the external magnetic field. It's external to the circuit, or to the loop, right? It's not really a circuit. It's just a loop of wire. So when we put the magnet in, so when we're pushing down on this magnet, in this direction indicated, there's an increasing magnetic flux. So increasing magnetic flux through the loop, that's down through the loop. Down through loop. So that's the cause here. In Lenz's law has to do with changes in magnetic flux. So we notice that anytime you change the magnetic flux through a loop, there's an induced current. So the loop basically doesn't like the fact that the magnetic flux is changing, and it's going to do whatever it can to prevent the change. So if there's an increasing magnetic flux down, the loop's going to do whatever it can to try and reject that field. So in other words, in addition to the external magnetic field, the loop itself can create its own magnetic field. And we call that an induced magnetic field. So notice how your book labels these two things differently. The magnetic field created by the magnet, that's the external magnetic field. That's sort of the cause of all this. The induced one right here, this is only responding to the change in the external field. That's the only reason it exists. That's why we use the word induced for that. So it's going to try to resist the change as best as it can. So if there's an increasing flux, if the magnetic field is getting stronger and stronger down through this loop, the loop is going to create its own current in such a way that it's going to be in the direction opposite the field. Because if it's getting stronger and stronger down, the loop doesn't like the change. And so it's going to produce its own field in the direction opposite. How does the loop do this? Well, what direction does the current need to go in this loop in order to create an induced field that points upwards? It has to go this way around the loop. So notice the direction of the induced current here. So looking down from above for this picture, it looks like it's in the counterclockwise direction. The direction of the induced current is to produce a magnetic field that opposes the change. Right? This is the gist of Lenz's law. So you can read this right here. The direction of the induced current is such that the induced magnetic field opposes the change in flux. So this picture right here it looks like it's the same setup, right? The magnet is in the same position, except let's imagine we keep it's sitting there at rest for a while, and then we try and take the magnet out. So we pull it up instead of push it into the loop. So what we notice there is actually the induced current is going in the opposite direction. Why would that be? Well, the external field that's going through the loop, the magnetic field from the magnet, is getting weaker and weaker. And the loop doesn't like that either. It doesn't like the fact that it's changing and getting weaker. So it's going to try and help it out. And it does that by by having an induced current in the opposite direction. So the induced current, if it goes this way because it's trying to create a magnetic field that's replenishing the decreasing external field pointing down through the loop. So what matters here, so this is a common misconception with Lenz's law. The induced field doesn't always oppose the external field. It's opposing the change. So sometimes, if the external field is decreasing in strength, it's going to try and help it out. If the external field is increasing in strength, then it's going to try and fight it. So it's just opposing the change. That's always true. So there's a list of possibilities here. If the magnetic field's steady, there's no induced current. If the magnetic field's increasing, then the induced field's going to fight the external field. They're going to be in opposite directions. If the magnetic field is decreasing in strength, then the two are going to point in the same direction. The induced current is going to try and restore the decreasing field strength. Okay, so a couple of directions just for practice with the directions. So take a look at those, and we're also going to get plenty of practice in class. Faraday's law is the magnitude of this induced field, magnitude of either the induced current or really the induced EMF is the more is the quantity that's directly calculated with Faraday's law, and then we can infer the induced current from using V equals IR. So the first part of this section is just saying as soon as we know one, we know the other. If we know the resistance in the circuit, so we can focus on induced EMF rather than induced current. And it's actually the induced EMF that's more closely related to the change in the magnetic flux. So actually, if you take the SI units for magnetic field, Webers, or Tesla times meters squared, and you divide by seconds, you actually get volts out of this. You actually get an EMF. And notice how there's actually no constants in front right here. So you could think of this as like defining how we get the Tesla in the first place. So we actually want this equation to be true, and then we define Tesla in order for this to be true. So we have to so if you're confused about why we define Tesla the way we do, why we have that U naught is equal to that weird constant, it relates to this being, kind of the starting point, because this is how we first saw that the magnetic field or magnetic flux, how that relates to the electric field, or the currents going around the circuit. Anyway, so this formula is used to find the magnitude of the EMF. Sometimes other books will write that the induced EMF is minus d flux dt. So this formula captures the direction and the magnitude. So basically, if you assign some direction for the circuit, you're also defining a direction, the normal direction that's positive. So fluxes that are in that normal direction would be positive and opposite negative, and then this is positive or negative. You have to include this minus sign to talk about this EMF, which if it's positive, then there will be an induced current going in this direction. So if you're careful with the right-hand rule, you could use this, which does the magnitude and the direction. But for our purposes, we're going to just use this for the magnitude and then Lenz's law for the direction. And that will always get us there. That's, for most students taking a course like this, that tends to be the easier way to do it, rather than trying to worry about both at the same time. One warning that your book gives is that if you have a lot of loops and you take a magnet and you're pushing it through like this, it's the total magnetic flux through the whole circuit. So if you have n loops, you have to multiply its n times the flux in any one loop. So you can actually get a pretty big magnetic flux, even if you have a relatively small area, if you just wind it over and over and over again. So we actually notice magnetic effects a lot with coils, just because we can get a lot of loops all at once. Yeah. Okay. So as a reminder, I'm going to rewrite this thing. Whoa. E. That looks even uglier than the other one. this is the magnitude of d by dt magnetic flux. And so I'm going to rewrite magnetic flux as it's B times A times cosine of the angle between those two things. So, whoa. So there are a couple ways. Where's your book talk about this? I guess there are a few ways you can change the magnetic flux, right? You could change, so B could change, which is what we saw before. We saw the moving magnet in the loop. We're changing the strength of the magnetic field, and that can increase the magnetic flux if you're bringing the bar magnet closer to the loop. But you can also induce a change by changing the area of the loop. Area could change. An example of this is this picture right here. So we have like a fixed sliding rails and then a moving just conducting rod. And if you'll notice that this loop, the area is increasing. The area of the amount of magnetic flux that's going through that loop, that conducting loop, is increasing. There's an increasing magnetic flux. And so from Faraday's law, if the magnetic flux is changing, there's an induced EMF. So the increasing magnetic flux into the screen will induce a current in what direction? Is it clockwise or counterclockwise? Maybe pause the video and give that a shot. All right, so there's an increasing magnetic flux into the screen. The circuit doesn't like that, the fact that it's getting stronger and stronger, so it's going to try and fight the change. It's going to create a magnetic field, an induced magnetic field that points out of the screen. And the way for it to do that is to create an induced current that points in the counterclockwise direction. Right? If you did the right-hand rule and you looked at the direction of the magnetic field like inside this loop, it would point out of the page, out of the screen, which will fight the change in the increasing flux that's going into the screen. So Faraday's law will help us calculate that. If we knew, so if, for example, if the area is changing, we could take so we quantify the area of the loop. So the length L is constant, but the distance X, which is like the width of this loop, is going to be changing over time. The strength on the magnetic field is constant. So if we look at this right here, it's the X that's changing over time. So when we take the derivative with respect to time of this quantity, we can take out the other two parameters, L and B, and dx dt is exactly how fast the rod is moving. So when we get VLB for the induced EMF, that's actually the exact same result that we got from the motional EMF equation. So Faraday's law generalizes motional EMF to also account for changing magnetic flux if B changes, which that we didn't see in the motional EMF formula. So Faraday's law explains everything in terms of like how changing magnetic fields relate to EMFs. It can explain motional EMF, it explains Lenz's law, it explains everything. I should probably end with it explains everything. So this is, so the end of the section is reiterating what I'm saying before. So Faraday's law, this is like the motional EMF part, but then there's also another part that motional EMF doesn't pick up. But Faraday's law tells us everything. Okay, so the problem is a problem from the book. The current in the solenoid is increasing. Okay, so we have to, Faraday's law is a statement about magnetic flux. We have to turn this statement about the current increasing to, okay, what's the magnetic flux through this loop doing? We're trying to figure out if there's a current in the conducting loop that surrounds the solenoid. Okay, so try and think of what's the direction of the magnetic field in the solenoid based on the current in the solenoid. You can pause the video and try that. So if you take your right hand and you wrap your fingers around the direction of the current in the solenoid, you'll find that the magnetic field inside the solenoid is going this way. It's pointing to the left. And remember, the magnetic field in the solenoid is approximately constant. So it's pointing to the left through this conducting loop that's surrounding the solenoid. So magnetic field is to the left, and this is the external, it's external to this conducting loop right here. this external magnetic field is increasing in strength. So remember the external magnetic field, the magnetic field due to a solenoid is mu naught n times I, the current of the solenoid. And we're told in the problem statement that the current in the solenoid is increasing. So therefore the magnetic field inside that solenoid is also increasing. So looking at it from the perspective of this conducting loop, there's an increasing magnetic flux through that red loop that's pointing to the left. So the loop, so what Lenz's law tells us is that the loop, the conducting loop, doesn't like the change in flux. And it does whatever it can to try and stop it. So there's an increasing magnetic flux pointing to the left. It's going to try and create a current that fights it, that points to the right. So the induced current in this loop is in such a direction that the magnetic field creates has to be pointing to the right. And the way for that to happen is for the induced current to be going this way. So this is I induced. So it looks like, looking at it from the left, like as in the picture, it looks like I induced points in the clockwise direction. All right. And if we actually wanted to, so if we wanted to keep this problem going, if there was like another part of the problem, if we wanted to know the magnitude of the induced current, we could set, so we would say that the induced EMF is the magnitude of the change in flux. And the flux is going to be, so I'm going to get rid of these right here. I'm just going to set the direction to the left. Well, I guess I'll keep them. I don't like writing the absolute value signs. If you don't like writing them, you probably understand why I don't like writing them. It's just ugly and a pain to deal with. Basically, it's like, it's just telling you ignore any minus signs that might pop up overall. Okay, so I guess I'll keep them just because I'm the teacher, so I should probably be good about this. The derivative with respect to time of the magnetic flux is the magnetic field. And I'm going to just go ahead and immediately replace mu naught and I from the solenoid. And for the area, it's the area not of this whole loop, but it's just the area over which the magnetic field is. So the area of the solenoid. So I'll write area of the solenoid right there. And it doesn't matter how many turns of the solenoid there are because we're looking at the induced EMF through just a single loop of the conducting wire. So there's no factor of like capital N or anything. So this is just magnetic field of the solenoid, B solenoid, or B external, same thing. Times a single, just the area, just pi r squared, where r is the radius of the solenoid, not the area, not the radius of the conducting loop. So all of these things are constant, mu naught n, the area of that solenoid, and then di dt is some value. And we're told it's increasing, so I already know that's positive. I can finally ignore these absolute value signs. So it looks like this is the induced EMF, and if we wanted to know what the induced current was, we would just have to say it's this divided by the resistance of the conducting loop. So it looks like it's mu naught n area of the solenoid divided by the resistance times this derivative, the rate at which the current is increasing in the solenoid. All right.